Good evening everyone. In this session we are going to discuss about the half adder and full adder in combinational logic circuit. So as we all very well know about what is combinational circuit and sequential circuit. So in combinational circuit the output depends on only with the present input, and in sequential circuit the output depends on both present and previous inputs. So here examples of combinational circuits are adder, subtractor, multiplexer, demultiplexer, encoder, decoder, etc. Examples for sequential circuits are like the output depends on both present and previous. It needs an memory circuit as an additional block in the circuit, right? So this memory device is used to store the predefined data to fetch and execute the next process. So here the example for sequential logic circuits are latches, flip-flops, registers and counters. All are 1-bit storage information devices. So this is all about the combinational and sequential logic circuits. Now coming to combinational logic circuit, the first example we are going to discuss is adder. So here this adder is of two types. One is half adder and another one is full adder. Before going to this half adder and full adder, we should know about that combinational circuit is a design process, whereas sequential circuit is an analysis process. So in design process we have to start with truth table and end with logic circuit. In sequential circuits, that is in analysis process, we have to start with logic circuit and end with truth table. This is the main difference between the combinational and sequential circuit, that is your analysis and design process. So here adder. This adder, coming back to adder is of two types. One is half adder and full adder. So half adder means we have two inputs and two outputs. Our input may be like A, B, that is based on users, right? But outputs are sum and carry. Outputs are sum and carry. Here we should recall your binary addition, subtraction, multiplication and division. But multiplication and division is not required here. We need to remember our binary addition and subtraction. We all very well know here we are adding two bits like A and B and two outputs like sum and carry. So here binary addition means for two bits like 4 combinations, 0 0 means 0 plus 0, sum 0 and carry 0. 0 1 means 0 plus 1 1, so your sum is 1 and carry is 0. 1 plus 0 means 1, your sum is 1, carry is 0. Here last combination is 1 plus 1, where we get 1 plus 1 is equal to 10. So your sum is 1 and carry is 0. So this is our binary addition. So this combinational logic circuit here performs an addition operation. All arithmetic operations can be performed. Here we perform an addition operation. So this is the truth table, as I said, 0 0 0 1, 1 0 1 1, and outputs are sum and carry. So this is the block diagram of half adder. Two inputs and two outputs. A and B are your inputs and sum and carry are your outputs. So now we have to find the boolean. As I said, it is a process of design. It is a design process. We have to start with truth table and end with logic circuit. So as a first process, we have to define the block diagram and then we have to frame the truth table. So now the block diagram and truth table is ready. So the next process is we need to end up with logic circuit. So in order to design a logic circuit, we need a boolean simplification, that is your boolean expression, right? So from this truth table we have to describe the boolean expression. We need to derive the boolean expression. So what is the relationship to derive a boolean expression from a truth table? we need to plot K-map. So the K-map is plotted for the outputs alone, that is your sum and carry, by using your inputs. So here we need to plot a K-map separately for both carry and sum. Two are outputs, both sum and carry are outputs. So we need to plot K-map separately for sum and carry. So the outputs is considered from the truth table. So where and all you are getting high input, that is 1, 0 is represented as low input and 1 is represented as high input. So wherever 1 is wherever 1 is available, that particular combination can be considered, and with that output we have to plot the K-map. So we know very well about the K-map. All adjacent ones can be paired. So since here we don't have any pair or as only two variable, right? So there is no possibilities for quad and octet. There is only possibilities for pair. If else there is no pair, we can consider it as isolation terms. So here we are receiving only isolation terms. We are attaining only isolated terms in sum and carry. So that isolated terms can be encircled. So this is the Boolean expression for here. We know how to frame a Boolean expression from a K-map. The concerned output where you are getting, there you have to mark 1, that particular box, and remaining all the cells should be represented as 0. So that particular box which you are having high input 1, you have to consider the box row and column, the concerned rows and column of that particular output box cell, right? So if you are getting 1 here, you need to, the box is like 0, 1, 2, 3. You have 4 boxes for 2 variable, that is 0, 1, 2, 3. So you are having output at 3. So the concerned cell 3, the concerned box 3, the row and column should be considered of the cell 3, so that you can get the Boolean expression as A, B. If it is complement, you have to, if it is 0, you have to put A bar. If it is 1, you have to put A. And also in column, if it is 0, you have to mention it as B bar. And if it is 1, we have to mention it as B. So likewise, we have to frame Boolean expression. We have to derive Boolean expression for carry and sum. So we get a Boolean expression, right? So by using this expression, see, in this expression you have carry AB and sum A XOR B. So with this expression you have to design a logic circuit by using logic gates. So in carry you have AB. AB is a AND gate option, right? AND gate operation. AND gate operation means multiple binary multiple process. And A XOR B, we know A XOR B, you have to use XOR gate. So here we need one AND gate for carry AB and one XOR gate for sum A XOR B, right? So by using one AND gate and XOR gate, we are designing the logic circuit of half adder. So this is the logic circuit of half adder. Sum and carry are your output. Inputs are A and B. So sum A XOR B represents this XOR gate, and carry is AB. From A and B you can connect the inputs for your carry, so that you are getting this output AB. So this is the logic circuit of your half adder combination logic circuit, right? And next full adder we can discuss in the next class. Thank you all.